All right. How's everyone doing? Yeah, pretty good. Excited. New week. More MR. I mean, what can you hope for, right? Best part of the week. All right. So, yeah, welcome EE225E. Woo! Talking about chapter 3. Everybody's good on the homework that's due today? Yeah? So quiet, everyone. Everybody okay on the homework due today? Seems like. Wow. Ekin, we've done well.
Yeah,
Very few
apparently.
questions. Yeah. Okay. Sounds good. So let's go at it. So what we're gonna start now is start chapter 3, which pretty much is again is kind of a maybe instead of a 10,000-foot view, it's more like a 1,000-foot view of MRI. And then we're gonna cover that, so you'll see similar things that we talked before, a little bit more in depth, a little bit more details. And then when you move to chapter 4, we're gonna start specifically more about the MR physics. Okay. Um, so let's start. So first of all, what the signal that we collect in MR comes from nuclei of atoms that contain either odd number of protons or neutrons. Okay, so those types of nuclei have what's called the nuclear spin and a magnetic moment, which inherently creates this phenomena which is called NMR. So that means that a proton, which is a hydrogen nuclei, would have a would be an appropriate one. What about helium? Helium H2. Well, H. What about helium? Would that would that work? What's going on? All right, can you hear me?
No, it wouldn't work. It has an even number of
Can you
protons.
hear me?
Yeah.
So I guess you can hear it, right? Yeah. Okay. Good. Okay. So helium has 2 protons and 2 neutrons, and so that's not going to work, right? So except if you're helium-3, which is an isotope of helium, which has 2 protons and 1 neutron, and that actually has an exhibits NMR phenomena. What about deuterium? Deuterium is I guess the nuclei of heavy water. So
Do protons and neutrons have the same spin?
um, well, they have spin 1/2. So actually, deuterium will have spin 1, which has some implications, but I don't want to, be out well beyond this class. But yeah, deuterium also exhibits NMR phenomena, albeit at a very different frequency of resonance than just proton. Okay, so what about carbon?
No.
Well, it depends.
Yeah.
Which carbon, right?
13.
Like the carbon 12, which is the isotope, the most common isotope, doesn't exhibit NMR. Carbon 11 is actually it's actually radioactive, but carbon 13 is a stable isotope and actually exhibits nuclear magnetic resonance. So you'd see a lot of work that's done on carbon 13 when you want to image inside the body or image metabolism and so on and so forth. Okay. All right. So it's the combination of this. It's the combination of this angular momentum and this intrinsic magnetic moment, which enables the NMR phenomena. And so there's this notion or this constant called the gyromagnetic ratio. And the gyromagnetic ratio is the ratio of angular momentum to magnetic moment, and that differs in different nuclei. So if you actually look at different type of nuclei, so hydrogen 1H will have is often used as a reference, so a relative sensitivity of NMR would be 1, but then it's a gyromagnetic ratio of 2 pi. When it's gamma over 2 pi, then it's represented either in hertz, kilohertz per Gauss, or megahertz per Tesla. So some of these units, so you could see 1H would be 42.575 megahertz per Tesla, or 4257 kilohertz per Gauss. So it gives you the relationship between the field and the frequency of resonance. Okay, so at 1 Tesla, hydrogen will precess at 42.575 megahertz. At 3 Tesla, then it would be 3 times that. Okay, so that's where we're getting to the 127.7 megahertz of 3T scanners. Carbon 13 has about fourth of that gyromagnetic ratio. It has certain implications in terms of its actually magnetization, but also at the resonance frequency. So it's really about 10 megahertz per Tesla. F19, so fluorine, it's actually pretty close to hydrogen, which is pretty amazing. Sodium 23 is another common nuclei that we use in MRI, even in NMR. And then 31P, which is phosphor, that resonates at, again, about third of the resonance frequency of hydrogen. Okay, so in order to perform an MR acquisition, we talked before, we have 3 different magnetic fields that we apply in order to create those images. Okay? And those are B0, which is the main field. That's the large field which creates the polarization. That's the strong, very, very uniform field. For a 3T scanner, it would be 3 Tesla, 7T scanner would be 7 Tesla, and so on and so forth. The B1 field, right, like you just increment this 0 into a 1, and then that turns into an RF. So this is the radio frequency field. It's called B1. And that creates the RF excitation that we talked about, that perturbs the magnetization into the transverse plane, perturbs that system, and in return, that system will emit a signal back and relax back into its original position. Okay, so this B1 field is at the resonance frequency, so it's at the megahertz range. If this is a constant field, this is an RF field, which is in megahertz range. And then B2, oh wait, there's no B2. So G instead, so the gradient fields are another set of electromagnetic fields, which you know, they do change, but they change at the audio frequency, and there's 3 of them. They're linearly vary the magnetic field in space, so we use them for spatial encoding, and we have GX, GY, GZ. All right, so far so good, nothing new. All right, so again, let's quickly talk about the B1 field. Well, it produces the polarization of a sample, M0. We put a sample in, and it will produce a polarization. So a net magnetization from an ensemble of spins will be created when we put a sample inside a strong magnetic field. And then the resonance frequency of that sample would correspond, omega would correspond to minus gamma B0, where gamma is the gyromagnetic ratio. Okay, so it is proportional, this angular frequency is proportional to the magnetic field. And again, for proton is 4.257 kilohertz per Gauss. And then other nuclei. By the way, N15 is an interesting one. It has a negative gyromagnetic ratio. What does that mean? Well, if you remember, if you remember this experiment, this particular one, because this wheel is rotating in a particular direction, then the precession is going this way. But if the wheel will rotate the other way, then the precession will go. Something is off with my thing. Can you see my screen?
Yeah, but can you
It looks
repeat
like
what you said, because the audio
it
kind
looks
of-
like it's stuck. Hold on. Yeah, sorry. It looks like my screen is stuck. So hold on. I'm gonna try to share again. Okay. All right. Can you see? So we had this video, and I don't want to play it because it's going to make sound, but it really depends on the direction of the wheel that I'm rotating will have an effect on the direction of precession. So if the wheel will rotate the other way, then it will precess the other way. So it's a similar thing that happens for nitrogen, where I guess the angular momentum of nitrogen is actually the opposite direction. And so from protons. So this is going to have a certain issue, because when we actually talking about excitation fields, we're actually talking about polarized field, so circularly polarized field. And so the direction, either where it's negative or positive, makes a big difference. So really, you really have to create an excitation with the right polarization, and the polarization needs to have a particular sign. Okay, so we're going to talk a little bit about that. But that's interesting. So what also it says is that the difference in, so this is 43 kilohertz per Gauss. So I guess it's 43, 40, let's see. It's about tenth of the resonance frequency of protons, but in the negative. So the difference in frequency is quite large. If you think of the frequency range, if this is proton frequency at 1 Tesla, that would be 442.57 megahertz. If this is zero frequency, the nitrogen will be, somewhere around here at minus 0.43 megahertz. Does that make sense? So it's a big difference between them. All right. So typical B0 that you see, anywhere anything below 0.5 T is considered low field. So 0.1 T is very, very low. 0.5 T actually have clinical scanners right now that are 0.5 T, and people are starting to make more and more. So there's a resurgence of low field scanners. 1.5 T used to be considered high, but now it's considered just standard. Okay, so standard field, where the frequency is 63 megahertz. 3T is high field, which is 127 megahertz. 4T is very rare. Actually, we used to have one at Berkeley, but it was decommissioned. So there's two. There's two. Do they still exist? Do you know the trailers, Anita? Or they were demolished? It was next to Tolman, where Tolman used to be. There were these two trailers. One of them had the 4T in it. So I'm not sure if they exist, but they might. And then ultra high field, which is 7 and above. 7 is actually FDA approved now, which only recently in the last couple of years. And there are also existing 9.4T and also 10.5T scanners. I think 11.6 is in the making or already existing. There used to be 11.6, but it quenched. Okay, so this is the B0 field. Now for spatial or spectral localization. So if you want to be able, so we're going to rely on the frequency for localizing where the spins are by changing the field versus space. But in order to do that, we need to have a very homogeneous baseline. And so the B0 field has a baseline of about 1 ppm. So when people one of the manufacturer will go and install a scanner, that magnet will come with about 40 ppm kind of accuracy. And then they'll go and install all sorts of what's called the passive shims. These are either metal leaflets or metal bars that you put on the sides of the magnet, and those help create a more homogeneous field by creating those disturbances. And during the installation stage, you'll see that the technicians will go and kind of like install these, run some calibration, and then have some software that would tell them, oh, you need to put this leaflet here and a leaflet here, or a piece of metal there, such that the field will be homogeneous. And they get to about 1 ppm, 1 part per million, which is pretty remarkable over a field of view of about 40 centimeter cube, which is really, really remarkable. Now, once you put a head inside or an object, the object itself is going to perturb the field further. So anything beyond 1 ppm really doesn't make a huge sense, because when you put a sample in, it's going to create more variation. Okay. So the dominated source of inhomogeneity is actually not the scanner inhomogeneity, but the fact that we put some body in there that creates these variation in magnetic field. How do I stop that video?
This is maybe a silly,
Yeah, go ahead.
a silly question, but how do you measure magnetic field in parts per million? Like I can imagine how you measure parts per million for a chemical that is in the air or something, but it's hard for me to imagine how you would measure the homogeneity of the magnetic field.
Oh, so so the magnetic field is accurate up to 1/millionth of a Tesla.
Mm-hmm.
1/millionth of 3 Tesla at 3T.
And do
Okay,
you have like
so
some sort of like, are you moving something around inside the space to try and measure the homogeneity, or can you measure it from the outside?
no, so actually what they do is they put very small vials of water,
Mm-hmm.
and then they go and perform these NMR experiments, and they look at different places in the volume. What is the resonance frequency? And this is actually a way to measure the magnetic field very accurately through NMR.
Gotcha.
So this is one of the ways. Or you can put a magnetometer, but the problem there is the accuracy of these magnetometers. They're not that accurate at those fields. You can have a very accurate magnetometer around Earth field, but at something that can measure parts per million accuracy, that's very difficult to make.
Mm-hmm. Cool, thanks. That
But
helps
you
me
can use NMR in order to do that. Yeah.
picture it. Yeah.
Actually, I will. Yeah, next time I will. Actually, when we talk in chapter 4, I will show some pictures of these devices that they put, because we took pictures when they installed the scanner. So, we talked about this before. We said, spins are kind of like bar magnets. And bar magnets, when you put in a magnetic field, they want to rotate, right? They feel a torque, okay? They feel a torque, but that's it. But the thing is, if the magnet would have rotated, if it had actually an angular momentum, then instead of rotating in this way, it would have precessed. Okay, that's what would have happened. Very similar to like this bicycle thing, which I don't want to show because it makes a lot of noise. So resonance is kind of like a spinning top if you think about it. It's pretty much a magnetization that goes around, and it wants to come back, but because it has an inherent angular momentum, then it precesses, and it precesses at what's called the Larmor frequency, or that resonance frequency, and it's proportional to the magnetic field. Okay, so we realize that once we put a sample inside a magnetic field, it creates polarization. If you perturb it, it starts precessing. But how do you perturb it? Well, for that, we use RF excitation of a B1 field, so it's an RF field, at the Larmor frequency, so at that particular resonance frequency, in order to excite those spins. Now, the field, the RF field, if we actually are looking at, let's say this is our scanner direction, right? So this is B0. This is B0. The RF field B1 is actually perpendicular to it. This is the direction of B1. Okay, so B1 is applied in the orthogonal plane to B0. Okay, so it's always orthogonal to the main magnetic field. All right. So and because it's RF, so it actually changes and oscillates all the time. So you can kind of think of it as the B1 field kind of rotates in the transverse plane. Okay. So we apply an RF field with a frequency omega 0 in the transverse plane. So it is applied in the direction XY as opposed to in the direction Z, right? We said that this is the Z direction, and this is the X direction, and this is the Y direction. Okay, so inside the plane. So we often model this as some, I guess, a phasor, if you think about that. So it's A times e to the minus j, so it's basically a complex harmonic, which is a good model, for this. So that precesses at a frequency of omega 0 t. Now, typical size of this B1, if you notice, are much smaller than the main magnetic field. So the RF field is somewhere between 0.14 to 0.35 Gauss. Okay, so it's much smaller than the RF field. In terms of its distribution in space, we try to make that homogeneous, but it's going to have about 10 to 20% variation throughout the volume. Okay, so from an accuracy point of view, at 1.5T is about 10%, and at 3T is about 20% variations throughout the field of view. The durations of that RF field is about typically 1 to 3 milliseconds, not more than that. Sometimes you'll have longer or shorter pulses, but those are the typical values. And the peak power that is applied in order to achieve those fields is ridiculously insane. We're talking about 20 to 40 kilowatts of peak power in order to produce that field. Okay. Just to illustrate, a microwave oven that operates, it would be about a kilowatt, right? Like a microwave oven is about a kilowatt. So we're talking about 20 times that in terms of RF energy. This is, quite a strong, it's like almost an FM radio station, like a broadcast FM radio station that transmits for, hundreds of miles. Now, let's see what is the effect. So if I have a magnetization that's pointing in this direction, and I'm going to apply a field in this direction. Okay. Now what's going to happen? What's going to happen is that this magnetization is going to be perturbed, but it's going to be perturbed in a certain way such that it's going to slightly move off its axis, but then it will start precessing. At the same time, it's precessing, the B1 field, because it's also an RF field, will also rotate and would always be at a very nice angle such that such that the contribution of its flip is going to add and add and add. And I'll show you this illustration. So here's kind of a video of showing how this magnetization is being perturbed. Okay, let me show you again. So in the lab frame, we're going to apply a rotating field, like a changing field in the transverse plane. And what's going to happen to the magnetization, it's going to start precessing, but for some reason, because we apply this field again at the same frequency, then it's going to tip the magnetization, and the magnetization is going to tip away from the main field and then rotate down. Now, how is that working? Well, there's certain ways that you can think about it. You know, there's a beautiful demonstration. I went to this scientific museum, like the Exploratorium, not Exploratorium, but somewhere else. And they had this really beautiful example. They had about 500 kilogram piece of metal hanging, like it's like a pendulum. And then they took, so it's basically pretty much something like this. You know, this is a tip, and here you have like a big weight, 500 kilogram. And then what they did is they gave you a refrigerator-like magnet, like a tiny one, connected to a string. And so you'd sit over here, and then you have a string with a small refrigerator-like magnet attached to this weight. Okay, so what are the chances of you moving that weight with this really tiny refrigerator magnet? I mean, that refrigerator magnet barely has any force applying, right? But if you pull very little, tiny, such that it doesn't, you know, so you just pull a little bit, then it would, you know, move this mass also a very, you know, just a tiny bit. Okay, and so it's going to move a tiny bit, and then this mass would then want to swing back and forth, right? But you're just going to swing a little bit. So what you're going to do every time that the mass is going towards you, you're going to pull a little bit, apply force. And when it goes back, you don't apply any force. And when it comes towards you, you apply a little bit of force. And as it turns out, because you only apply the force when the mass coming to you, then you can move this 500 kilogram quite a bit with this really tiny refrigerator magnet. And this is what's called resonance, because you're applying this force exactly at the natural frequency that this mass is oscillating at. And this is kind of what the phenomena that happens here. We're applying those tiny forces such that the magnetization we want to process around this B1 field, and this B1 field is rotating every time with the magnetization such that this effect is accumulating. Now, this is hard to see in the lab frame. So what we're going to show you is I'm going to show you this in a rotating frame. So I can actually go and describe the exact same thing in a rotating frame. So now, here in the lab frame, the RF field was rotating, and this was precessing, right? But now I'm going to actually have a rotating frame. So in the rotating frame, we rotate with the B1 field, such that in the rotating frame it stays in a stationary direction, and so the magnetization will do too. So in the rotating frame, the B1 field will stay stationary. The magnetization, once it starts processing, it also processes at exactly the same frequency as the rotating frame, so it's also not going to move. So in the rotating frame, you can basically ignore all precession around this axis. And really, the only field that is being in effect is this field. And if you apply this field, then what a magnetization will do is, of course, precess around this particular field. And so this is really what's happening. Okay, in the rotating frame, this is the motion that happens. And really, the magnetization is precessing around the B1 field. In the lap frame, the B1 field is the B0 field is affecting, so everything is kind of rotating around kind of two axes, and it's a very complex motion. But in the rotating frame, again, it's only a motion, it's only a rotation around the B1 field. So this is a really nice way to interpret of why applying a radio frequency field exactly at the Lamour frequency will tip the magnetization, because the magnetization will effectively just rotate around this B1 field. Isn't that amazing? Now, if we rotate at a slightly different frequency, then, this nice coherence thing, like the nice thing I described with this mass, that I only pull when the mass is coming towards me and I don't do anything when the mass is going away, well, that could change and it's not going to be very efficient. Like if I pull at a different rate, then there's just no way for me to move the mass because I'm just not in sync with it. And in the same way, if I apply a B1 field not at the Lamour frequency, then it's not going to efficiently perturb the magnetization. So the only way to really efficiently perturb the magnetization is applying a radio frequency at the Lamour frequency exactly. That would be the most efficient way, and then it would just be a rotation. Any questions? Any questions? No questions?
Professor, so I see there's like 9.
Grad student, yes, grad student.
Maruf, yeah. So
why? You can call me Mickey then.
Oh, okay, nice. Thanks. So why is there 90-degree phase difference between the B1 field and the the tilted magnetic field, I guess? Yeah.
Well, I mean, if you think about it, the magnetization again precesses about. I mean, just imagine that if the magnetization is pointing in this direction, right, and you have a B1 field in the rotating frame, it's kind of like this is stationary, right?
Yeah.
So this is a magnetic field that's stationary in the rotating frame, and you have a magnetization here, and so the magnetization will want to align with this B1 field, but it also has magnetic moment. So what it will do, it will start precessing around this B1 field. And that's why if I apply a B1 field here, then the magnetization will precess this way. In a very similar way, if I just apply a B0 field and perturb, then it would, precess around B0, right?
Oh.
But because we're looking at the rotating frame, then any rotation around B0 is canceled because we're rotating with it. So that is canceled. So whatever is left is, as the only field that is effectively left is the B1 field, and we're just rotating around the B1 field.
Oh, so it's like the white line is rotating around the B1 field.
Yes, the magnetization will rotate around this. Absolutely. Yeah,
okay.
And that's what's happening.
Thank you.
In the rotating frame, right?
Yeah.
In the lap frame, it's actually behaving, quite a bit it does the spiral thing. It's a complex motion. But in the rotating frame, this motion is very simple. So we'll work with that. We'll do a lot of this analysis by moving back and forth from rotating frame into lap frame and so on and so forth for easier analysis. Okay, so this RF excitation at the Lamour frequency is often parameterized by a flip angle. So how you're going to apply this for a certain amount of time such that you're going to get a certain angle that is accumulating because of this precession. Okay, so for example, a 90-degree pulse would move this magnetization into the x direction. Okay, so that would be a 90-degree pulse. If I move it down, there will be a 180-degree. If I move it just like here, that will be 10 degrees, and so on and so forth. Typical, again, B1 fields is 0.14 to 0.35 Gauss. The duration is about 1 to 3 millisecond, which, by the way, it's a very long time at 64 or 128 megahertz. If you can kind of think about it, if you think about it, let's see, 1 millisecond at 64 megahertz. How many cycles is that? So 1 second will be 64 million. So divide by 1,000, that's 64,000 cycles happen in 1 millisecond. Okay, so if, let's say you do a 90-degree excitation that flips this down into here in 1 millisecond, during that 1 millisecond that I went here, in the actual lab frame, it actually rotated 64,000 times till it got down there. Okay, so 64,000 times it rotated till it went down there, and at 3T, it will rotate 128,000 times. That's a lot of time at those frequencies. Okay, so you can actually calculate what is the rotation around the B1 field. Well, according to the formula, the angular frequency is gamma B1, right? The rotation around B1 is gamma times B1. What is gamma times B1? Well, it's 4.257 times 0.16 Gauss. This is kilohertz per Gauss. This is Gauss. And so I get pretty much 0.68 kilohertz, which is also 680 hertz. So the rotation speed around the B1 field is about 680 hertz. Okay, so it's very slow compared to how much it rotates around B0. Does that make sense?
I have a quick
And
question.
from that, yeah, go ahead.
Sorry, why isn't there a negative sign out front in this equation, but there was one for B naught? Is that just like a sign convention or like a direction convention?
Yeah, no, actually it should be negative, to be honest.
Okay.
Yeah, but the sign doesn't make a difference here for that calculation.
Gotcha.
So in this particular case, if I just want to figure out what the frequency, whether it's a positive frequency or negative frequency, it makes no difference. Okay, but you're right, it should be a negative sign here. There you go. Okay, and basically when I say minus, that means that it rotates clockwise as opposed to rotating counterclockwise. That's basically what it's saying. All right. Yes. Sweet. Okay, so this is pretty cool. So so if I apply this type of field, right? So that gives me the frequency. Then from that I can actually infer, if I apply this field, like how long I need to apply it such that I'll get a 90-degree pulse. In order to get a 90-degree pulse, I need to apply it for 367 milliseconds, pretty much. Okay. If I apply this thing at 367 milliseconds, that would correspond to a quarter of a rotation, which would result then in a 90-degree flip angle. All right. Okay. So then magnetization, then, if you remember, relaxes. And we talked about the two types of relaxation, T1 relaxation, which is the longitudinal component relaxation. And those are somewhere between 10 milliseconds all the way to about 2 to 3 seconds. Okay, so depending on the type of tissue. And a transverse relaxation, which is the transverse component, And that is decays at a rate of about, well, it could be less than 10, but we usually don't see those species so much. So it's 10 to 300 milliseconds approximately. This is the time constant for the decay in the transverse direction. And this one is the recovery in the longitudinal. And if you just remember, the longitudinal T1 corresponds to the filling of the tank in the toilet, and the transverse relaxation is the loss of signal. So the transfer component is the loss of signal, is how fast the water in the bowl kind of decays, disappears. And as it turns out, T1 is always bigger than T2. And from an energy point of view, that's always true. So while we always like to think about them as decoupled, T2 can never be bigger than T1. Okay. They could be equal, but well, it's always less than equal to T1. All right. And this is kind of the trajectory in the rotating frame. This is the trajectory in the rotating frame of how the magnetization relaxes. And again, I'll plot it. Okay. So it's kind of like, it's kind of like you bend and then go up, if you look at my picture. Now in the lap frame, the relaxation is again, more complex. So this would be the behavior. Oh. Yeah. So this would be the trajectory that the magnetization will go through when it relaxes in the lap frame. So it's the opposite way of, excitation, right? Excitation, it goes like this. And then relaxation, it will go then back up, and again in a similar trajectory. Kind of like, all right. Okay, so we also mentioned before that when you have a magnet that's rotating, this magnet's rotating creates a magnetic field that changes versus time. And so the magnetic, or if you think of the magnetic field lines, changes. So if I put a coil or a loop next to the sample, the fact that the magnetization rotates will create changes in the flux, magnetic flux going through the loop, and will induce an electromotive force, EMF, in that coil, basically a voltage that we can then pick up. And so if I actually look at the signal that I'm going to get, it's going to look something like this, right? It's going to oscillate at the Larmor frequency, and it's going to decay over time with T2. Okay, so after excitation, this is the signal that I'm going to get. And this signal is called a FID, or free induction decay. Okay, free induction decay, because we're not interfering with it, it is inductively coupled, right? The magnetization is inductively coupled to the coil. And so this is what we're seeing, a free induction decay over time. Now, if I know what the frequency is, I can actually demodulate the frequency by multiplying it, by basically demodulating that frequency. And after demodulation, I remove this oscillation effectively, and I will see just a signal that decays. And this is equivalent. If I perform demodulation, this is equivalent to looking at the rotating frame, okay? Because that's, again, it's the same frequency as the rotating frame. Does that make sense? So the voltage after demodulation in the coil is going to look something like that over time. Okay, that's the envelope of that signal. Okay, so we talked about B0, we talked about B1, we talked about relaxation and also the received signal. Okay, now we need to think about how do we perform localization. So potentially we could have maybe imaged using the B1 field. If B1 field was selective in space, so let's say I have a magnet, right? And I apply the radiomagnetic field. But let's say I put like a tiny RF coil inside, and that tiny RF coil only sees a very small part of the sample. It doesn't see the entire sample. So using this excitation, I can actually excite only part of the sample. Okay. The problem is if I want to go then an image inside the sample, then I will need to take this coil and pretty much inject it into the sample and then apply an RF field, right? So that's going to be a problem if I want to create an image of the entire body. I'll have to pretty much cut the body into pieces, put a coil next to each one of them, and then perform an NMR experiment. That's not invasive, right? That is very invasive. Okay, so the B1 field, because if you actually think of what is the size of the wavelength of this B1 field, well, at 64 megahertz is about half a meter in tissue, so it's 50 centimeter inside tissue. Okay, so it's pretty long. So it affects pretty much the entire volume. So there's no variation of that field inside a volume. Okay, so has very poor localization. So that's not a good way of localizing the signal. Instead, what we do in order to localize the signal is we actually use gradients, right? We talked about that. And the gradient, they create changes in BZ versus the axes. So remember, we're only looking at the change in the magnetic field in the Z direction, but the gradient in X changes that magnetization versus the X direction. The Y gradient changes the BZ magnetization, BZ field with respect to Y. And then the Z gradient changes the Z field with respect to Z. So it's always a field pointing in the Z direction, but it changes spatially in its intensity versus X, Y, or Z. Okay. Now, when we try to generate such fields, we actually, as it turns out, according to Maxwell equation, it's impossible to generate a field like that. It is impossible. That field will also have some component that are going to be dBy to dx and also dBx to dx. So it will create also fields in the direction y and in the direction x. But turns out, but those are constant fields, and they're not contributing to precession, so they're actually not they're not a problem. They're very small and they're not an issue almost whatsoever. So these are called concomitant fields, and if B0 is large enough, then these are turns out to be negligible. And we're going to talk about concomitant fields a little bit further when we talk about artifacts and imperfections. So we'll get to that. Okay, so when we apply a gradient field, the resonance frequency changes in space. So it kind of looks like this. At the center of the magnet, the resonance frequency is omega 0, right? That's proportional to B0. And then because we're applying a gradient field on top of that, then the field, let's say on the right, is going to be higher, and the field on the left is going to be lower. So the field distribution in space, or the field distribution, and as well the resonance frequency distribution in space, is going to be a function of x when we apply an x gradient. And it's going to be omega 0 plus gamma gx times x. Gx is the size of the gradient, x is the position, and then gamma is the gyro-magnetic ratio. Okay, so as I move further away, then I would have a higher field. Now that is proportional to the gx that I'm applying. What if I apply a stronger gx? What would happen? What would happen if I apply stronger gx? Well, how would this map change
Slope would
of resonance
increase.
frequency? Yeah, the slope would increase. Yeah, so a stronger GX, it's going to look like that. Actually, this is too much. If you remember, G is really much smaller than omega 0, right? So it's really not drawn to scale. I mean, I should have did something here, like as if it's, this line over here should have been like way outside. It's pretty much like, it'll be like 10 meters away from me or something like that, and the slope is going to be small. So this is not drawn to scale. What if I put a negative GX? So I'm
Hey,
applying a GX.
I have a question.
Yeah.
This relates to Amit's earlier question about the negative sign. Did we just
Mhm.
forget about the negative sign, or is there a flip in this gradient, or?
Well, you just have to be consistent, I guess. And I guess I wasn't very consistent here. So I think we're just gonna use gamma to be, yeah, I guess you're right again, that this should have been probably negative. The frequency would be negative gamma. I guess it will be negative than that, right? So then, thanks for doing that. So then pretty much this would be the effect, right? And then if I apply a negative GX, then it would be in the other direction. You just need to be consistent and track it. Basically, your image will be flipped if you don't track it correctly. Okay, because you'll be mapping positive frequencies to negative and so on and so forth. But you're absolutely right. Now, what about the sizes? So the sizes of these gradients are about 1 to 10 Gauss per centimeter. What does that mean? Well, 1 centimeter, when I apply 1 Gauss per centimeter, that means that 1 centimeter away from the center, I will have a field of 1 Gauss. Okay, that's what it means, 1 Gauss per centimeter. 2 centimeter away, it will be 2 Gauss. 3 centimeters away, it will be 3 Gauss, and so on and so forth. Okay, so it's a gradient field. So really far away, like maybe 30 centimeters away, well, there will be 30 Gauss. Okay, so it's just increasing in space. Other units are millitesla per meter. So the fields are typical scanners will have anywhere between 1 to 10 Gauss per centimeter. Our 3T scanner has 3.3 maximum Gauss per centimeter. Okay, that's the 3T GE that we have. The Siemens has 4 Gauss per centimeter as its maximum, and then the 7T I think will have 10 Gauss per centimeter, if I remember it correctly. Okay, so these are the typical. Another unit that you often use is millitesla per meter. So it's about 10 to 100. So 33 Gauss per centimeter, 3.3 Gauss per centimeter is 33 millitesla per meter. Okay, and that also corresponds to about 4.2 to 42 kilohertz per centimeter. So if you remember, through gamma, field Gauss is translated into hertz. Okay, that's the relationship. All right. The waveforms, if you actually look at those gradient magnetic field, we switch them on and off in order to do imaging, and we change them in somewhere around the audio frequencies. So they change not very fast, up to about 5 kilohertz on and off when we switch them. Now, how fast? If I tell the scanner now, I want you to apply 1 Gauss per centimeter. Well, you can't create that instantaneously. It will take time for that field to be created, to ramp up. It cannot be created instantaneously. And so this is defined by the slew rate. The slew rate is how fast the field changes. And that is described as Gauss per centimeter per millisecond, or as Tesla per meter per second. So how fast this thing changes. Okay. And so this could be an issue from a safety concern, because once you have a change in the gradient, that also causes change of magnetic field versus space. And so it creates a magnetic changes in flux that can cause changes in electric fields, and that causes eddy currents, and that can cause in the body peripheral nerve stimulation at some rates. So you can actually stimulate neurons if you switch these things very rapidly. Okay, that
Quick
can actually
question.
happen.
Does this also happen with the B1 field, since that's also a changing magnetic field?
No, it doesn't happen with the B1 field. B1 field, first of all, it's much lower in terms of its intensity, but it also much higher frequency. And there, it doesn't cause peripheral nerve stimulation, but it can actually cause heating in tissue.
Okay.
Okay, so its interaction is different. Yeah, thanks for that. So it can actually cause RF burns and also heating if you're not careful. For the gradients, we're talking about very big amplifiers, lots of voltage, lots of amps, because you need to create those really large changes. In order to have those huge slew rates, you need to put a lot of currents into these coils. So switching magnetic field generate electric field that can stimulate nerves. Yeah, overlap here. Sorry about that. But there's kind of like an FDA limit on what's possible. Which is dB to dt is less than 20 Tesla per second. Okay, so this is this is the FDA limit on the slew rate. But often, people will model this, or they'll perform experiments with different sequences that you have those switches, such that you make sure that you don't stimulate peripheral nerves. And with some scanners, the gradients are so strong that you can actually create not even peripheral stimulation. You can actually stimulate, let's say, the heart, which could actually cause death. So you got to really be careful there. I've had like my back muscle stimulated using some sequence, and sometimes people see flashes in their eyes when they do it, in particular for EPI sequences like fMRI. fMRI is a very typical sequence that you get a lot of stimulation and also diffusion. Yeah. So if you actually look at IRBs, this is some of the things that are described, is that you could actually have magnetic stimulation happening. So when you consent a subject to go through MRI, you tell them that. Now the gradients are supposed to be linear. So they're supposed to, for example, the Z gradient, supposed to, as a function of Z, to change its intensity in a linear way, but that's actually not the case. And you'll see that it's linear across a certain field of view, but then after that, it kind of rolls off a little bit. So there is some nonlinearity, and we have a homework question about that, because that's going to have an effect on your ability to get the right geometry of the image that you're going to create. Because remember, we map frequency to position. If we assume that the gradients are linear, then you think that something is going to be at a particular frequency and is going to map to a particular position, but because the gradients are nonlinear, then it's going to map to a different position. Right? This actually happens a lot, and this is an example of a body. This is a cross-section, a coronal cross-section through a pediatric patient body. So a coronal is kind of like as if I would slice myself like this. Okay, and this is a coronal section. This is the liver. This is the bottom of the heart. This is the aorta. This is the aorta, and this is the iliac arteries that split down. These are the bowels. And to be honest, the body, even of a child, should be straight. It shouldn't look like this barrel. But the thing is that the gradients, as you move up here, become weaker in this direction. And because they become weaker, then you get this geometric distortion. And you can, of course, correct for this geometric distortion, which it's called gradient warping correction. And this is the result after the correction. Okay, so it is possible to correct for it, albeit you're going to lose certain things. For example, you're going to still lose resolution around this area because when we correct, we perform an interpolation, but interpolation doesn't bring you resolution. So there are some implications for that. We're going to talk more about that when we talk about system imperfections later.
I
Just
have a
want to give you a
question.
heads up on homework too. Yeah.
So for these nonlinearities, or for these like effects that we see, is it proportional to the field of view? So if we have a smaller area that we're imaging, will we see the effect less?
Yeah, absolutely. So over a small field of view is very linear, but as you move out, let's say 20 centimeter out, 30 centimeters out, then you start seeing a lot of nonlinearity. Yeah.
Okay, thank you.
Okay. So how do we create an image? Well, we place a sample in this field. And so what would happen is that you're going to have magnetization start developing as you put the sample in. How long does it take to develop? Well, about 5 times T1s, right? Because it's exponentially increasing up to a certain value, right? It's like the tank filling up. So 5 times the time constant T1 is enough to pretty much create the magnetization. So it's not instantaneous. MZ doesn't develop instantaneously. Usually it's not a problem because you're going to put a subject in, you're going to move it into the bore, and then it takes time for you to prescribe a sequence. It's more than 5 seconds to prescribe a sequence till they move into the magnet, so it's not a problem. But there are some situations that I've seen that definitely researchers didn't take that into account. In particular, when we do a flow experiment. In a flow experiment, you have a bore, and then you have some reservoir of water, and then you have a pump that flows water into the scanner and then out, and you want to image the flow inside. Well, what happens if the flow goes this way and it doesn't spend enough time inside the magnet? Then the water doesn't magnetize, and so magnetization is not created, and so you get garbage. So what people do is they actually take the pipe, and then they roll it in a little bit inside so that the water spends enough time in the magnet such that it magnetizes, and that is fine. So it's something to be aware of, definitely, if you're doing flow experiments. Okay, so you put the sample in B0, then you excite using B1, and when you excite, you create some transverse magnetization. That transverse magnetization immediately starts processing. Okay, so and what we're really interested in when it starts processing is just the MXY component, just the transverse component of magnetization. That induces an EMF in a coil. Okay, and so this is the signal that we pick up. And in order to encode the position, we apply gradients, and that changes the frequency versus position and kind of creates this effectively 1D projections, right, that we saw before. Okay, so this is kind of the idea. Okay, so there are some limitations. First of all, if we apply either a gradient strength or gradient duration, that will correspond to the resolution that we'll be able to see the position. If you think about this, if I apply a very strong gradient, then I map the same space into a wider range of frequencies. So I'm able to resolve those frequencies with better resolution, right? Because I map it to a larger space. The other way of doing things is just applying the gradient for a longer duration. So if I look at a sequence, let's say I observe a particular sequence for a short amount of time, there's kind of like an inherent ambiguity of me to be able to determine what that frequency is. It's the time frequency uncertainty, right? I observe a signal over a short amount of time, then I don't have a very good spectral resolution. If I'm going to observe it over a longer time, then I will be able to get a much higher spectral resolution. So these two things, the gradient strength and the duration, are going to affect my resolution. At the same time, your signal decay. And because the signal decays, that's going to also limit your ability to get resolution. If you have diffusion, that also going to create some decay. And if you have field inhomogeneity, which we're going to call T2 star later, which you don't right now, you don't know what even it means, but all these things are going to have some limit on the resolution. The typical resolution that you get in MRI, in imaging and clinical scanner, is about 1 millimeter. If you're looking at very small animal scanners, it's going to be about 20 microns. Okay, so because there the gradients are much stronger and much faster, so it's easier to do. But for clinical scanner, it's maybe about 1 millimeter. You can get less than 1 millimeter, but that's pretty much the a typical clinical level of resolution. So here's some examples. Let's look at an example of how things work. Let's say I have a one-dimensional object, MXY, and that object is a rect. And it's a rect that is 10 centimeter wide. So it goes from -5 centimeter all the way to 5 centimeter in the x direction. Okay. Then I'm going to apply a gradient. I'm going to apply a gradient field, which will create a variation of that frequency in space. Okay. So my frequency is going to change in space. So the question is, if I now apply and excite this magnetization here, I'm going to excite, what's going to happen? Okay. The signal that I'm going to get is going to be proportional to MXY. And because I have a big coil that I'm going to put next to the sample that have a uniform sensitivity, I'm going to receive signal from the entire volume at the same time. Okay, so the signal is proportional to MXY, and I'm going to receive a signal from the entire volume at the same time. So by creating this field distribution, what I'm going to get is a signal that this part of the sample is going to emit a low frequency, this part of the sample is going to emit a high frequency. They're all going to add in the coil together. Okay. All right, so let's think from a mathematical point of view. What am I getting? Well, the magnetization at some position, let's say at this position over here, and this is position x0. What this magnetization at this position going to emit? Well, this magnetization at m0 at x0 yes, at x0 is going to I have some magnetization there, right? And then that magnetization starts precessing. And when it precesses, it produces a harmonic. Okay, so I can represent that harmonic as a complex harmonic. We're going to talk why it is a complex harmonic. But you can also take the real part of that, but we're just going to represent it as a complex harmonic. And the signal that is going to, so this magnetization is going to precess at a frequency omega0 plus gamma gx times x0. Okay, so this is the signal that this particular part of that volume is going to emit. Does that make sense? So all the magnetization that's over here is going to emit some signal that its frequency is proportional to omega0, but also to gx times x0. So a magnetization, let's say over here, let me change color. At the edge of the object, a magnetization at the edge of the object What type of signal is going to emit? You're muted. If you want to say something, then unmute yourself. What type of signal this green magnetization is going to emit?
It's going to be higher frequency.
Yes, higher frequency. And that higher frequency is pretty much corresponding to omega 0, which is the same, plus gamma gx times x1, right? X1 is higher than x0. This is x1. It's higher than x0, so the frequency is going to be higher. Okay. Now, the signal in the coil, though, is going to be the sum of all of these. So what I'm going to do is I'm going to integrate over space. Okay, I'm going to integrate over the entire x, and then I will receive the signal that I will receive in the coil. So the signal received at the coil is the integral over x of mx e to the minus I omega 0 plus gamma gxx t dx. Okay, so integral over the entire thing. Okay, but now you stare at this long enough and then tell me if you don't recognize anything here. I mean, this looks like something. What does it look like?
Fourier transform.
Kind of, not exactly a Fourier transform, right? Like a Fourier transform would have e to the minus kx times x, right? That's what it would have. Here I have a t, I have omega 0, so it's not exactly the same. But it has a Fourier form. It has a Fourier form. And so remember, this is a function of t. It's not a function of k, where's spatial frequencies here? So what we're going to do is we're going to massage things a little bit. So this is S of t. S of t is the integral of all of that. But now if you actually look at e minus I omega 0 times t, that is not a function of x, right? So I can take this e to the minus I omega 0 t outside of the integral. Okay, so this is a constant. Like this is not a constant, but it's, you know, it's not in the integral, so I can put it over here. Does that make sense? All right, so I did that. So now what I want to do is I want to make this look like a Fourier transform. It's almost a Fourier transform, except that I have a gamma gx and t. And I want to represent it something else, like in some spatial frequencies. So what I'm going to do is I'm going to multiply by 2 pi and then divide by 2 pi. Now, why do I do that? So I multiply by 2 pi and then divided by 2 pi. Why did I do that? Well, because the Fourier transform has a 2 pi, I 2 pi, right? So now this kind of looks like a Fourier transform. This looks like something times x. So, you know, I'm almost there, right? Like this looks like a Fourier transform. This is right. But this, if I would have just called this k, if I would just call this thing kx, then that would look like a Fourier transform, right? If I would call gamma over 2 pi gx times t, if I would call that kx, I'm done, right? And that's exactly what I'm going to do. I'm going to call kx gamma over 2 pi gx times t, and then I'm going to put it over here. It is a function of t. It is a function of t, but it's a variable, right? It's a variable, which is a function of t, but now it has a Fourier form, okay? So effectively, if I stare at this long enough, what you would realize is that the signal that I'm measuring is e to the minus I omega 0 t times the Fourier transform of m of x, the Fourier transform of m of x, because this is by definition the Fourier transform, evaluated at k, a specific spatial frequency, which is gamma over 2 pi gx times t. So for different times, I will have different spatial frequencies. Okay, So kx changes linearly with time. Okay, so my signal is, again, the Fourier transform of mxy evaluated at spatial frequencies gamma 2 pi gx times t. Probably some of you are familiar with this one. Classic. Okay, so let me just try to finish something here. So again, this is my signal, and this is what I've this is what I just derived, pretty much by heuristic. Now, if m of x is rect, then the Fourier transform of m of x is a sinc, right? If m of x is a rect, like we had before, right? This is a rect, then the Fourier transform of it is a sinc. Okay, so the Fourier transform of it is a sinc. So effectively, if you think about it, what is the value of kx? What is the value of kx? For time equals 0, immediately after excitation, kx will be 0. And as time goes by, kx increases by this proportionality. Kx has a unit of 1 over centimeters. So as we go over time, then we actually collect data in the frequency domain. So if the data is a sinc, if the Fourier transform of our object is a sinc, then effectively, what I'm going to actually collect, this is the data that I'm going to be collecting. It's e to the minus I omega 0t. The real part of it, is going to, oscillate with an envelope of a sinc. If I actually multiply this by e to the plus I omega 0t, then I cancel those oscillations. This is a demodulation, and I would get what's called the baseband signal, which is pretty much half a sinc. How did I get half a sinc? How did I get half a sinc? My object was erect. The Fourier transform of it is a full sinc. But when I excite, when t equals 0, k equals 0. So the signal that I'm going to get is going to be the signal here. And then as time goes by, I move for positive kx's. This is kx. And so I just collect this data and this data and this data. And so my data would look like half a sinc. Okay? Because I'm applying a positive gradient. What if I would apply a negative gradient? Well, then my time signal would correspond to this part, right? Would correspond to this side of the Fourier transform. But because in the fact that we have something symmetric here, it doesn't really matter so much for this particular case, but it will matter eventually. Okay, so here's the point. If I now get this signal and I compute a Fourier transform of that baseband signal, if I compute, this is the signal that I collected, I compute a Fourier transform. So by the way, this is the signal I collected. What are the axes? Well, the axis is time, but it also kt, right? Time, but it also kt. K versus time, right? Time and k corresponds to some function of time. It's a linear function of time, right? So spatial frequency and also time. So the time signal represent the spatial frequencies. It's kind of like a little bit out there. When I compute a Fourier transform, then I almost get a projection of that object. But because I only collect half of the frequency domain, I'm going to have a large imaginary component over here. So it's not a perfect projection. So computing a Fourier transform of that would give me, you know, a real part which looks like a rect, and then kind of like an imaginary component that looks like that. So it's almost, this is almost an image if I compute a Fourier transform of it. It's almost an image. It's not perfectly an image, and we'll get to kind of how to fix that I guess on Thursday. Okay. So just to kind of like illustrate some of the key points here, we had an object that was erect. Let me just stop this for a second. Hold on. Yeah, we had an object which was erect. Its Fourier transform is a sink. We showed that if we apply a gradient field and excite, then we are effectively collecting data in the frequency domain of this object, and starting at k equals 0 and then going positive over time, right? So this is kind of what we got. We got that the signal that we get is proportional to the Fourier transform of our object at k's that are increasing in time. And so if the object is erect, then my signal that I'm going to get is a modulated kind of modulated sink. If I demodulate by that factor, then I'm going to get a real sink that I'm going to collect. And then if I take a Fourier transform of the signal, I'm going to almost get the image back, but not perfectly because I only got pretty much half of its frequency domain as opposed to got both sides. Okay, does that make sense? So this is a little bit of a subtlety that we didn't touch last time. And we're going to try to fix on Thursday to figure out, first of all, how do we get the other part of that frequency domain, because that may be crucial in order to create an actual image. And what happens actually in 2 dimensions. All right. So we're going to continue that on Thursday. All right. So have a good evening. Good luck on your homework. Homework 2 is going to be posted tonight. Ekin, any comments on homework 2?
I guess I'm planning to go over probably the first problem in the homework tomorrow during discussion. So if everyone can at least read through or look at it before discussion, that would be great.
Okay, and then there's a programming part. And the programming part, basically what you're going to do is you're going to play with Fourier transforms of sinks and jinks to create pretty much what's called a numerical phantom. It's you're going to create objects such that you can evaluate the frequency domain and then reconstruct them by computing an inverse Fourier transform. And so you're going to simulate through that kind of an object. And you're going to build an object that looks like a face out of boxes and circles that in the frequency domain are designed using modulated sinks and modulated jinks. Okay, so you're going to basically do that. And courtesy to some of our former students that took a class, as well as John Tamir, who's a faculty at UT Austin, we have 2 options for you to solve this problem. One in MATLAB, for those that like programming in MATLAB, and the other one is in Python. So we created both a MATLAB kind of worksheet as well as a Python notebook for you to go through. So pick your own poison and enjoy this exercise. Hopefully you'll really digest kind of like the shift theorem and the modulation theorems of 2D Fourier transform, and kind of what happens when you try to sample the frequency domain, how those look like, and what's aliasing, and so on and so forth, based on the object size. All right. So see you on Thursday.